Photovoltaics is a technology that enables the direct conversion of sunlight into electrical energy. The fundamental principle is the photovoltaic effect, in which incoming photons of light knock electrons out of the atoms of a semiconductor material, generating an electric current. This phenomenon was first described in 1839 by French physicist Alexandre Edmond Becquerel during experiments with electrochemical cells. It was later studied by other scientists. In 1873, Willoughby Smith discovered the photoconductivity of selenium, and in 1883, Charles Fritz built the first functioning solar cell with an efficiency of about 1%. The modern era of photovoltaics began in 1954, when Bell Laboratories produced the first silicon solar cell with an efficiency of around 6%. Paving the way for practical applications of solar panels. The basic component of every photovoltaic system is the solar cell. It is made from a semiconductor material, most commonly silicon. Semiconductors have special properties. They conduct electric current under certain conditions, but act as insulators in others. Silicon is used in monocrystalline or polycrystalline form. Monocrystalline cells have higher efficiency and a uniform structure, while polycrystalline cells are cheaper to produce but less efficient. The operation of a solar cell is based on the creation of a so-called PN junction. This junction is formed by combining two types of semiconductor, type P, which has an excess of holes, positive charge carriers, and type N, which has an excess of electrons, negative charge carriers. At the boundary between these two materials, an electric field is created. When photons of sunlight hit the cell, their energy releases electrons from the atoms in the material. The electric field in the PN junction directs these electrons in a single direction, generating direct current. The current generated by solar cells is direct current, DC, meaning it flows in one direction. Most electrical appliances, however, require alternating current, AC, so the electricity from the panels is fed into an inverter, which converts it into AC. A complete photovoltaic system typically consists of several main components: solar panels, an inverter, cabling, and in some cases, batteries for energy storage. The panels are connected in strings, and their total power output depends on the number and efficiency of the individual cells. The performance of a photovoltaic panel depends on the intensity of sunlight, the angle at which the light hits the panel, and the panel's temperature. Higher temperatures paradoxically reduce efficiency because they increase the material's resistance. For this reason, photovoltaic systems are designed to provide good ventilation for the panels and set them at an optimal tilt relative to the sun. The efficiency of commercial panels today ranges from 15 to 22%, while the best laboratory cells can reach over 40% when using special materials and multi-layer structures. An important parameter of a photovoltaic cell is its open circuit voltage and short circuit current. These values are used in system design to achieve optimal performance and compatibility with other components. The lifespan of high-quality photovoltaic panels typically ranges from 25 to 30 years, with power output gradually declining by about 0.3 to 0.8% per year, depending on manufacturing quality and operating conditions. A photovoltaic system can be configured as either an off-grid or an on-grid system. Off-grid systems operate independently of the power grid and store energy in batteries. They are used in remote areas, on cabins, in mobile applications, or wherever there is no access to a power line. On-grid systems are directly connected to the public power grid, and any surplus energy generated is fed into it. In such setups, a mechanism called net metering is often used, where the amount of energy fed into the grid is subtracted from the amount taken from it, effectively lowering electricity bills. In addition to these basic types, there are hybrid systems that combine elements of both. These systems allow energy to be stored in batteries for self-consumption, while also sending excess electricity to the grid. Such solutions provide greater energy independence and resilience during power outages. A key component in these systems is the modern lithium-ion battery, which offers high energy density, long lifespan, and low losses during charging and discharging. The amount of electricity generated by photovoltaics depends on several factors. Geographic location is critical. The amount of sunlight varies with latitude and climate conditions. Areas with higher solar irradiance naturally achieve greater annual energy production. Another factor is the orientation of panels relative to the sun and their tilt angle. In the northern hemisphere, south-facing panels capture the maximum sunlight throughout the day. The optimal tilt is usually between 30 and 40 degrees but can be adjusted for seasonal optimization. For example, increasing the tilt in winter for better performance when the sun is lower in the sky. Shading is another important factor. Even partial shading of a panel can significantly reduce its output because the cells in a panel are usually connected in series, and shading one cell restricts the current in the entire string. To minimize this problem, panels are installed in locations free from obstructions such as trees, buildings, or poles during key sunlight hours. Modern systems use bypass diodes, which allow current to flow around shaded cells, reducing power losses. Photovoltaic panels are designed to withstand harsh weather conditions. Silicon cells are sealed between protective layers, a front layer of tempered glass that resists hail and mechanical impacts, and a back protective film. The assembly is sealed to prevent moisture ingress. The panel frame, usually made of aluminum, provides structural strength and allows for easy mounting on support structures. Electrical connections are protected against corrosion, with durability matching the expected lifetime of the panel. The inverter, also called a converter, is a crucial component of any photovoltaic system. It transforms the direct current from the panels into alternating current suitable for powering appliances or feeding into the grid. The quality of the inverter has a major impact on overall system efficiency. Modern inverters also offer energy production monitoring, fault diagnostics, and real-time performance optimization. There are central inverters for large-scale installations, string inverters for medium systems, and microinverters installed directly at individual panels to reduce shading losses. Maintenance of photovoltaic systems is relatively low effort. Panels should be regularly inspected and, if necessary, cleaned of dust, pollen, or bird droppings, as dirt can reduce efficiency. In regions with frequent rainfall, panels often self-clean, but in dry or dusty climates, cleaning several times a year is recommended. Monitoring system performance is also important to detect and address drops in output, which may indicate technical faults. Photovoltaics is constantly evolving, introducing new types of solar cells and technologies that increase efficiency while reducing the cost of electricity production. In addition to traditional silicon cells, there are thin film cells made from materials such as amorphous silicon, cadmium telluride, or copper indium gallium selenide, CIGS. These cells have lower production costs, are lightweight and flexible, making them suitable for installations where conventional panels would be impractical. Their disadvantages include lower efficiency and shorter lifespan, but advancements in materials and manufacturing processes are gradually narrowing this gap. Another direction in development is multi-junction cells, which combine different materials with varying abilities to absorb different parts of the solar spectrum. This approach increases overall efficiency because each material optimally utilizes a specific wavelength range. Laboratory multi-junction cells have already reached efficiencies exceeding 40%, and the technology is steadily approaching commercial deployment. Perovskite solar cells are another promising innovation, offering high efficiency at relatively low manufacturing costs. The main challenge remains their stability and resistance to moisture and UV radiation, but ongoing research is aimed at overcoming these limitations. Photovoltaics can be used not only in the form of classic panels on rooftops or solar farms, but also as part of building materials. Building integrated photovoltaics, BIPV technology, allows solar cells to be integrated directly into roof tiles, windows, or facade panels. This not only generates electricity but also replaces traditional construction materials, reducing overall building costs. Examples include solar roof shingles and transparent photovoltaic glass that combine aesthetics with functionality. From an energy systems perspective, photovoltaics plays an increasingly important role in the transition to renewable energy. The growing share of solar power in the energy mix, however, brings challenges, especially in balancing production and consumption. Solar energy depends on the time of day and weather conditions, which requires the development of energy storage technologies and smart grids. Battery storage systems, pumped storage power plants, and demand response technologies help stabilize the grid and maximize the use of generated energy. The economic viability of photovoltaic systems has improved significantly in recent years. Falling panel prices, increasing efficiency, and incentives such as subsidies or feed-in tariffs mean that investments in photovoltaics can often pay for themselves within 5–10 years, depending on system size, electricity prices, and local conditions. After the payback period, the system continues to produce electricity at minimal operating costs, generating pure profit for the owner. Photovoltaics also has a major role in humanitarian and development projects, providing electricity to communities without access to the grid. Portable solar systems can power lighting, water pumps, communication devices, and medical equipment in areas where building traditional power infrastructure would be too expensive or technically impossible. Combined with energy storage, photovoltaics offers a reliable and clean power source that improves quality of life. The future of photovoltaics is tied to further miniaturization, efficiency improvements, and cost reductions. Wider adoption of solar solutions in households, businesses, and industrial facilities is expected, as well as integration with electromobility and combination with other renewable sources. Technologies such as floating solar farms, solar roads, and hybrid systems combining solar panels with vertical wind turbines may further increase the share of renewable energy and reduce dependence on fossil fuels. Photovoltaics is becoming one of the pillars of sustainable energy for the 21st century.